as we get back into the concrete side of linear algebra for the rest of today, we want to talk about what it means for a collection of vectors, a bucket of vectors that somebody hands us, to be what's called linearly independent. That's the main sort of topic that we want to be talking about for what we're about to do. And so just to get us a sense of what that is supposed to mean for us and why we should expect that it will be a meaningful concept for us in linear algebra, let's take a look at how this section begins. So we'll get started in this section by considering the following quick activities. So here are two sets of vectors. The first set, S, has two vectors in it, 2, 3, 1 and 1, 1, 4. And the second set has three vectors in it, two of which are the same as the vectors that are in S. And so the question is, if I take the spans of these sets of vectors, is one of them going to be bigger than the other, or are they the same size? That's the main question that we want to kind of investigate. So if I want to put the span of the vectors v and w, remember what the span is it's the set of all possible linear combinations. So some parameter times v plus some other parameter times w. And I'm going to let those parameters range over the real numbers. So for the sake of my plot here, let's say we let s go from minus 10 to 10 and t go from minus 10 to 10. But in practice, of course, they're going to range over all possible real numbers. And so the span of these two vectors looks like this. Right? It's a plane that contains those two vectors in it, my vectors u and v. So then the question is, if I throw a third vector into that mix, right, and my third vector is this one, will the new span of those three vectors be bigger than or smaller than or the same as the span of my originals? So what do you think? If I put this third vector on the screen and sort of give us a good look at it, maybe we'll get a sense of whether the new span of these three vectors is bigger or smaller or the same as the span of the original two. Adding new vectors into my set that I'm using to span is never going to give me a smaller span. It's never going to give me a smaller vector subspace than the original span. But it could give me something larger. So what are the circumstances under which I can expect to get a larger subspace when I span? Well, let's take a look. Is it true, for example, I'm going to zoom out on this a little bit so we can see it a little bit better. What can we say about the relationship of my new vector to my two old vectors?
Is it falling on the same plane? I'm having a hard time telling.
Let's see if maybe we could zoom in on it a little bit or something just to tell, because that is the right question to ask, right? Does this new vector reside in the same plane as my original two? And to me, it kind of looks like it does. But to know for sure, we probably have to do some kind of a calculation, right? We have to find out whether it's possible for there to be some linear combination of the first two vectors, 2, 3, 1 and 1, 1, 4, that is exactly equal to the third vector, minus 1, 0, minus 11. So what's our tool for answering that question? How can I convert that into a vector equation?
We could make an augmented matrix and then your REF.
Yes. So to find out whether minus 1, 0, minus 11 equal to a linear combination of the other two vectors, well, we can just write out that arbitrary linear combination as some multiple, let's call it x1, times my first vector, 2, 3, 1, added to some other multiple, let's call it x2, of the vector 1, 1, 4. So that's a vector equation. And if that vector equation is consistent, then the answer will be yes. So if consistent, then minus 1, 0, minus 11 belongs to the span of these vectors. And if not, then it doesn't. And as you said a minute ago, our tool for actually answering this question is to convert this vector equation into an augmented matrix. 2, 3, 1, 1, 1, 4. And then on the right-hand side, negative 1, 0, negative 11. And then we have to go in and find the reduced row echelon form of that thing. And so for that, I will go into a Sage cell, This is also the tool that's available to you in the textbook. And I'll just ask for the RREF of the matrix, which would have 2, 1, -1 as the first row, and 3, 1, 0 as the second row, and 1, 4, -11 as the third row. And see what that spits out. Try to zoom in on this as much as I can. There we go. So there's my RREF. And so when I put this in its reduced row echelon format, can I tell, is this a consistent system of equations? I'm going to put my little augmented matrix decoration around that.
Yes.
It's consistent. How can I tell?
The last row we have 2, 0.
The last row is all zeros. If it were an inconsistent system, we would have ended up with some sort of contradiction, like zeros on the left side of the bar and then a 1 on the right side of the bar. 0 equals 1. That's a contradiction. But this one is a consistent system. In fact, if we converted it back into its equation form, we would have x1 equals 1, x2 equals -3. And in fact, we can check that 1 times my first vector, so 1 times 2, 3, 1, minus 3 times my second vector, 1, 1, 4. We do out that arithmetic. 2 minus 3, that's -1. 3 minus 3 is 0. 1 minus 12, that's -11. So it works out. So indeed, my third vector is already in the span of my first two. And so what does that tell us then about the span of these three vectors compared to the span of the first two of them? What should we conclude? So the spans must be the same, because my third vector is already a linear combination of the first two. I'm not going to get anything new out of the linear combinations of those three that I couldn't already get from linear combinations of the first two. Right? So not only are span of S and span of T the same size, they're actually the same vector subspace as one another. They're all of them equal to this same two-dimensional plane that we have here. And so the vocabulary that we want to build around this example is that we want to say that this set of three vectors is linearly dependent. Right? There is a linear combination of some of the vectors in my set that produces for me one of the other vectors in my set. Specifically, my third vector is a linear combination of the first and the second. Right? It's one of the first one plus -3 of the second one. It's only in the case where none of my vectors are a linear combination of the others in the set that we can say that the set is a linearly independent set. So linearly dependent means that there is redundancy, right? That I don't need my third vector in order to span what the first and the second vector can already span, right?